Hello there, Calculus fans. Going to talk about hyperboloids. It's a pretty interesting topic. The challenge for students is that there are three types. There's a hyperboloid of one sheet, hyperboloid of two sheets, and there's the hyperboloid we don't call a hyperboloid, the degenerate hyperboloid, which we call the cone or double cone. In terms of traces, it goes like this. So let's say I say x squared minus y squared plus z squared equals 4. You can do the same thing we talked about before, which is if you fix x, in other words, if you pretend that this is a constant, you could identify the name of that 2D graph. And then if you fixed y, you treated that like a constant, you could identify that shape. And if you fix z, you could identify that shape in 2D. So let's do that real quickly. What are the names of those curves in 2D? Well, you can see that this is both are squared, and there's a minus. If both are squared and it's a plus, it's a circle or an ellipse. If both are squared and it's a minus, it's a hyperbola. Okay, so let's talk about the naming convention. I'll show you some pictures of this in a second. Here, both are squared, but with a plus. That's going to be a circle. And that's actually the key to the naming, is right here. It's a circle, and not only that, it's a circle that always makes sense because that's positive. Like, it doesn't matter what's in that spot there. It's going to be positive. So it's a hyperboloid of one sheet. And then this one, hyperbola. So it's easy for me to remember because two of the traces in two directions, it looks like a hyperbola. So it's a hyperboloid. And the other direction is a circle, and it always makes sense. This is positive, so it's a hyperboloid of one sheet. Now, interestingly, I picked one where y was where the circles are, which is like this picture you're seeing in the corner of your screen, this picture here. That's one where the circles are around the y-axis. Okay, so now let's do one more standard. Here's one that's around the z-axis. That's a hyperbola of one sheet, and I've played around with the numbers. Let's erase this. And a natural question could be, well, how skinny is it in the middle? So let's draw that for a second. I'm going to fix the z, and I'll make the z 0. If I can do it. And that's how skinny it is in the middle. Now, in this case, that particular one I'm giving you is x squared plus y squared minus z squared is 1. So that radius in the middle is just 1. You can see that if you cover up the z, it's a circle of radius 1. If I change the numbers, so the way we often write this is it's written with some numbers possibly in front. We write it, again, the textbook has this clever way of writing it so that it doesn't change the fact of whether it's positive or negative. They write it this way. So let's tweak those. Look what happens when I make b larger. It makes it an ellipse on the ground. Part of the reason it looks funny is because I'm zoomed way in. Let's say I make a larger. It just changes that radius in the middle. If I make them the same, so if I make like a2, and I make b2. Now it's just a circle of radius 2. There you go. And the way I have it drawn, it's chopping it off in kind of a funny way. So that's all that does, tweaking the a and b. The c scales it vertically. So if I increase the c, it goes up more. That's all it does, stretches it out a little bit. The general naming, though, is quick. If this is positive, then it's hyperboloid of one sheet. Okay, what happens if we make that 0? X squared plus y squared. Well, then the smallest radius is 0. And just for ease of discussion here, if I kept everything else the same, and this was 16, then the smallest radius would be 4. Let's do that real quick. I'm going to make the numbers 1 again. A is going to be 1. B is going to be 1. C is going to be 1. And now I'm going to make the number on the other side 16. So that makes the radius in the middle 4. So if you make that 0, it's a circle of radius 0. Here we go. And that's that degenerate hyperboloid. And I'll show you the traces in a second. In fact, maybe I'll show some of the traces now. So let's go back to the previous one. Like here are the traces if you fix an x. Let's watch them as you go by. They're hyperbolas. They do change directions. Hyperbola that way, hyperbola the other way. Cool. If we do the traces for y, hyperbola, hyperbola. In two directions, it looks like a hyperbola, from this side and this side. And then lastly, from above, what can we say? From above or below, it looks like this. Circles or ellipses if we adjust. That's going to be true for all of these shapes. The only difference is how skinny it will be in the middle. So if you make it a 0 on the other side, then it just gets skinnier. Now, there's a small comment here, which is that in the very middle here, get rid of a couple things. It's actually 2 lines. That's something I emphasize more later in the term, but you can see technically that's not a hyperbola. It's like a degenerate hyperbola. And so even though this one looks like hyperbola, hyperbola, and it also looks like from the front and the back, this one's technically not a hyperbola. When you get to 0, it's 2 lines, but everywhere else it is. So I still say the traces as hyperbola, hyperbola, circle. Okay, last one. If I say x squared plus y squared minus z squared, and the other side's a negative, like -4, then it breaks apart. It doesn't make sense when z is 0. You can see that when z is 0, there's nothing. So let's do that. So now I'm going to make k -4. They break apart. The traces still work out the same way if you look at it this way. The traces are hyperbolas. Hyperbolas, 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 hyperbolas. If you look at it from y's perspective, hyperbolas, hyperbola, hyperbola, hyperbola. If you look at it from z's perspective, circles. So it's just the fact that there are no circles unless z gets big enough to overcome this. In fact, you can even anticipate what it is, because right here is z equals 2. That's when you first touch it. How do I know that's when z is 2? Well, because if I put a 2 in here, then I'm going to have x squared plus y squared minus 4 equals -4, and the 4's cancel. So you sort of need z to be big enough to get there. So that's the idea of hyperboloids. I think of all of those as the same thing. You just have to remember that that special case when it's really skinny has a name, a cone. But my favorite thing about this visual is the following. I feel like this looks like a lava lamp. So if we tweak the numbers, and I'm going to show you this in a second, and we allow it to oscillate, here we go. So here's k equals -5, -4, -3, -2, -1, 0. Get that cone. 1, 2, 3, 4, 5, 6, and back down. It's pretty cool, I feel like. That transition from hyperbola to 1 sheet to hyperbola to 2 sheets. It's just a question of what's the radius at the skinniest place. For a cone, the radius is 0. For the hyperbola of 1 sheet, here the radius is 4. And for hyperbola of 2 sheets, the radius doesn't even make sense until z is 2. So there you go. A few other notes. There are many hyperboloids of 1 sheet. If you search around, this is very prevalent in architecture and in practice. The cooling towers of a nuclear reactor Various lighthouses, the Kobe Port Tower in Japan, St. Louis Science Center. There's just so many examples. Cathedral in Brazil. People like this shape. A place in Manchester where they built the walkway to look like that. Pretty cool. I did want to say one thing here. I'm going to leave that for another day. So a cool thing about these, been working on some 3D shapes. This is not officially a part of our discussion. Okay, one last thing, which is kind of fun. Imagine you have a hyperboloid of one sheet like this, and you make strings that go up and down that are stretchy. And then you start rotating the bottom, but leave the top the same. A cool thing happens. You actually get this shape. At some moment, you actually get exactly the hyperboloid of one sheet. Let me add a few more so we can see it. It's a cool little visual of a hyperboloid of one sheet. You can make it as skinny as you want. So if I let time go, it will go all the way down to a cone, which is pretty interesting. So let's make it match up. There we go. One of the many interesting facts about hyperboloids. Okay, hope you found that interesting. All right.